Welcome to the 10th class meeting of the Introduction to DSP. The first announcement is about homework 10. It covers class meetings 8 to 10 and will be due on next Tuesday. Here goes the overview. We are covering chapter 3 on the Z transform. And hopefully we may finish this one next Tuesday, or if it is covered well, then today. Here goes the messages from instructor. I have graded your MATLAB homework problems and found that about the square root Nyquist pulse related MATLAB homework, many of you just copy and pasted the explanation or discussion provided by LLMs, and they hallucinated. So the parameter beta, or sometimes alpha or gamma, depending on which source you use, the rotor factor of the SRRC, square root raised cosine pulse, determines the bandwidth of the pulse. And what you need to remember is that if beta increases, bandwidth of the pulse also increases, which means that the square root raised cosine with larger value of beta may have higher frequency component, which means that it may change faster than the case with smaller rotor factor. But many of you wrote exactly opposite. Probably you used the LLMs that hallucinated. So be careful. It would be a very, very useful tool for you to write up the kind of skeleton of what you want to write, but the details may be totally wrong. Not just some part is incorrect, but just your LLM may give you exactly opposite answer. In that case, we engineers may have some disaster. So be careful. That's the message from me. Here goes the review that includes the reviews of the previous class meeting and previous class meeting, because Z transform is so important. According to my experience, the most of the confusion arises from the fact that we ignore the definition. So the definition of the Z transform of a discrete time signal xn is given by this infinite sum, which may contain Z raised to the power of positive integer or negative integer. Even though we simply write this way, actually for the exponent 0, we do not consider Z to the 0. We just define Z to the negative 0 in this definition as 1 always. Got it? And this definition may give us some convergent sequence, convergent summation or non-convergent summation. And if we call the set of complex numbers on which this summation converges, we call the set as the region of convergence. And this serves as the domain of this function capital X. This is the definition. And sometimes The Z transform of a discrete time signal may be much simplified by using the geometric sum formula. But when we use the geometric sum formula, always we have to be careful about the fact that the common ratio, whose absolute value of the common ratio must be less than 1, otherwise that formula cannot be applicable. That's what you have to remember. So some discrete time signals have simplifiable Z transform using the geometric series formula. But when you separate one infinite sum for two signals, you have to be careful. So suppose you want to compute this infinite sum, and somehow you find x is summation of two signals, y and z, and you are very tempted to replace x with y and z, y plus z, and to rewrite the infinite sum as the sum of two infinite sums. From here to there, it's okay. But from here to there, you must be careful. This is very important. One of the just a second, let me check. Okay, let me continue. So one of the sufficient condition for you to rewrite a single infinite sum into sum of two infinite sums is that each one gives you a conversion. So if this converges and that converges, then you may say that summation of these two is the same as this infinite sum. But be careful, ready? Anyway, so we will see that again and again. And what you need to remember is also this one. Suppose you have two signals, x1 and x2, both has the same base and exponent, but one is right-sided and the other is left-sided. Like this. Then you can find the Z transform having the same algebraic expression, but with the reason of convergence totally different. And as you see here, the algebraic expression of the Z transform does not uniquely determines the original signal. This must be remembered. This example is so important. By the way, here in this case, Z is not, okay, so let's do it first. So when you have some confusion, just write the infinite sum. So you have x negative 1, sorry, there is no negative 1. So you have 1 plus az to the negative 1 plus az to the negative 1 squared dot dot dot, which means that z is not allowed to be 0. And as you see here, z equals 0 is excluded in your use of geometric sum formula. And here, if you rewrite capital X sub 2 of z, you have negative a negative 1 z plus a negative 2 z squared dot dot dot. And as you see, there is no z to the negative 1, so z equals 0 is allowed. So no problem to have this one. By the way, when you write this way, actually, something very alarming, and probably what you want to do is not this one, but something different. So if I remember correctly, from this one, you may write it as 1 minus, and what is the common ratio? This is the common ratio, and the first term is this one. I hope I'm right. Just a second. 1 minus, I believe so. And then here, not this one, but that one. Okay. You multiply a, then you have a minus z, and here negative z, and this is z divided by z minus a. Got it? So I'm sorry, this part is totally wrong. But when you rewrite the z transforms of x1 and x2 as a rational function in z, then they have the same form. Got it? So be careful and remember. By the way, there was some interesting notion of pole zero cancellation, and you may have some idea, but we will see more today. So if you still don't have quite clear understanding, then it's okay. By the way, I also mentioned that when we talk about the location of poles and zeros, sometimes we consider extended complex set, which includes infinities, because in complex numbers, you may have different directions to reach infinity. But anyway, in that case, I will write that set as C bar to distinguish it from the set of complex numbers with finite modulus or finite absolute value. Another one is that some discrete time signals do not have Z transforms. We will see today. Last time, at the end of the class meeting, I just covered it very fast, but while reviewing, I found that's very important, so we will see this. And similar to what I already told you, algebraic expression or pole zero pattern, pole zero diagram, pole zero plot does not completely specify what was the DT signal or even the reason of convergence. So you cannot uniquely determine what was the your Z transform actually, because ROC is a defining part of the Z transform. And here goes the previews about next sections. We will cover inverse Z transform, which I introduced the definition last time, and some Z transform properties like linearity, time shifting, modulation, differentiation, conjugation, blah, blah, blah. And even though I may not be able to cover this part, since I have emphasized a lot of times about your application of the knowledge learned in this course to your high school math, especially about the Fibonacci sequence, I have put the MATLAB homework problem already to generate the Fibonacci sequence. And also this time you will see in homework 10, you derive the kind of poles of the Fibonacci sequence as a discrete time signal. Anyway, so let's see. So here goes an example. You have a discrete time signal, x of n, and let me ask you a question. Is this x well defined for every n? So for every integer n, is this well defined? Means this sum is okay, does not blow up or something. And for every n, either this part is 0 or that part is 0. And you have finite number in the exponent. So this signal x is well defined. So x of n is well defined. So we have a smiling face. Now, second, what is the Z transform? Of course, it would be great if we can find a closed form expression, but it's not necessary, right? Sometimes we may not be able to simplify that infinite sum, even though it is well defined and it has some reason of convergence that is not empty. So first, well defined. Second, derive capital X of Z, possibly with a closed form expression and the reason of convergence. So let's do it. So we have the first term and second term, and we are very tempted to apply Z transform to each term. And we know from this one, just substituting A equals 1/2, we have the Z transform of the first term like this. Am I right? And as we've seen already, for A non-zero, we have that one. Or this one, right? So it appears that, it's okay. We have two convergent infinite sum that has very good closed form expressions. So the textbook just temporarily write the Z transform as this one. But actually, precisely speaking, this is not correct yet. Because the reason of convergence for the first transformation is this one. And the reason of convergence for the second part is that one. And if you plot the reason of convergence is on the z-plane, what happens? The first reason of convergence is outside this circle with radius 1/2. And the second reason of convergence is inside the circle with radius 1/3. What does that mean? The second term does not converge on the set of Z that allows the convergence of first term, and vice versa. So in order to write Z transform as the sum of these two, both of them converges, but only one of them converges. What does that mean? You cannot write it this way. You just cannot write this way. Then what can we write about Z, capital X of Z, the Z transform? Z transform has what? The reason of convergence, the empty set. In that case, we do not say, hey, capital X of Z is 1, 1 minus 1 half Z inverse plus Z, Z plus 1 third. And for Z empty set, we do not write it this way. Some people love to write this way because if we write this way, by specifying the ROC is 0, then actually we can reconstruct the signal X from this information. However, many of the textbooks and many of the authors of the textbooks just say that this signal does not have the Z transform because the domain is an empty set. What's the use of a function that does not have any element in the domain? For example, you may say that, okay, f of x equals sine x, and x in empty set. G of x equals cosine x, x in the empty set. As functions, these definitions are meaningless. Got it? So, following this idea, we have to say that the Z transform of this signal does not exist. But for convenience, some people say that this is the Z transform and that is the ROC. But sometimes I agree and many times I don't agree. Anyway, got it? So this is an example with these two basic examples showing that some of well-defined discrete time signals may not have Z transform. So Z transform is not always well-defined. Got it? And now here goes some example. Okay. Suppose you have a pole zero diagram like this. So there are 3 poles and you have a unit circle so that you can see that, hey, 3 real positive poles with value less than 1 and value greater than 1. The problem is that from the properties of the ROC may be outside this largest radius pole like this, or inside this smallest radius pole, or between A and B, between B and C. We don't know which one is correct. So specifying just the pole zero locations, in this case pole locations, does not allow us to uniquely determine what was the signal. Got it? So you must be very, very careful when you handle Z transform. Z transform is not just about specifying the algebraic expression. You have to also specify the reason of convergence. Got it? Okay, so here goes the inverse Z transform. And as I already told you in the last class meeting, the original definition is in terms of the contour integration on the complex Z plane. And similarly, you have inverse discrete time Fourier transform that is a finite interval integration of dtft times e to the negative j omega n, something like that. Anyway, even though the definition looks horrible, fortunately, in many cases, not always, but in many cases, we love to use rational functions in Z for this one. So this is kind of always applicable because this is the definition. But we are not using this contour integration to find the sequence from the Z transform, but we prefer using well-known properties of Z transform we've already seen. So there are many tricks to compute the inverse Z transform, but we will see three methods. Just inspection, which means that, hey, I know this, something like that, and very famous partial fraction expansion, sometimes abbreviated as PFE. And the last one is the power series expansion. We will see examples. So first, we know that a to the n u of n, the right-sided exponential, has this Z transform. And the reason of convergence given by the outside the circle with radius a. And we have another signal that has a negative of a to the n and u of negative n minus 1 that has basically same form except that it allows z equals 0. So this may be more preferred. So they are the same, okay? So using this, and here, memorizing this result, you can, by inspection, find the inverse Z transform. So let's see. Suppose X capital, sorry, is it right? Yeah, capital X of Z, the Z transform of some signal, we don't know. So Xn has the Z transform, capital X, that is given by this one. So you have a rational function in Z inverse. And here, this is the key. The reason of convergence is absolute value of Z greater than 1/2. Now, the question is find X of n. And now, you don't want to plug in this algebraic form here. And you don't want to somehow incorporate this reason of convergence in your contour integral. You don't want to do that. What you want to do is to just use this famous right-sided, left-sided exponential signals, Z transform. So here, you find an expansion. Actually, this can be said partial fraction expansion, but anyway, so you do not know yet what is capital A1 and what is capital A2, but if this is the same as that one, what should be true? You multiply the denominators and multiply that one, blah, 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 and you can find capital A1 and capital A2. So it's like this is -1, this is 2. Now, from the pole 0 plot, what do you have? You have the pole of this one located at 1/4. And pole of that one located at 1/2. And you already know that your signal has region of convergence in this region. So when does this kind of gives you some region of convergence that can be that can include that one? Of course, Z greater than 1/4. And what about this one? Z greater than 1/2. And if you intersect, then you have that one back. So from this knowledge, you have -1. So you have -1 and 1/4 raised to the power of n, un. And what about that one? You have 2 times 1/2 raised to the power of n u of n. Then you are done. Got it? So this is partial fraction expansion combined with inspection method. Got it? Here goes another example. So unlike the previous one that has here 1, the very, very simplest polynomial in Z inverse. Now you have second order polynomial in Z inverse in the numerator and another second order polynomial in Z inverse in the denominator. What do you do? One high school method is by inspection again. The numerator is written that way and denominator factorized. Now you see why some electrical engineering professors say that, hey, you students in our department, bring me any chapter in your high school. I will tell you when you use in electrical engineering. So this finding roots of polynomials even used in electrical engineering. By the way, if you really want to have a challenge, then let's have one. So you just, after the class meeting, come to me and say, hey, professor, some part in high school is this one. Do we use it? And I will provide answer in the by the next class meeting. And if I'm successful, you pay me how many money? How much money? 50,000 Korean won. And if I cannot find, I will give you 50,000 Korean won. How about that? Anyway, so it's just a joke. And the reason why I say this joke is that, as I say, almost every mathematical knowledge you learned in high school is used in electrical engineering. Anyway, one of the methods is this one. You have so-called long division. Means you divide the numerator with the denominator. And easily you will see that the quotient is 1/2. Sorry, 2, because this times 2 is that one. So you can immediately rewrite capital X in that way. So the key is that you have less ordered polynomial in Z inverse in the numerator. Got it? So you have constant and first order, second order in Z inverse. And then you apply partial fraction expansion to the second term. So you find two coefficients, A1 and A2. And by comparing this part with that part, you can somehow find these two numbers. So what do you have? Now it's time for you to use inspection method. What is the Z transform of 2? Delta 2 times delta of n, right? So this is. What about this one? And what about that one? When you consider this outwards region of convergence, causal exponential signals. So you convert this one as causal exponential signal, and you convert that one also causal exponential signal. So you have negative -9 and 1/2 raised to the power of n un and 8 times u of n. Got it? By the way, what if I do not give you this region of convergence? Then it's kind of you have to consider which direction your region of convergence is. So there are 3 possible signals. Without this, you find 3 signals. Actually, you can find 4 signals. In that case, ROC is simply the empty set. Anyway, here goes an example with power series. So suppose your signal x of n has z transform that has 4 factors. And each one is a polynomial in z or polynomial in z inverse. Since you have finite number of factors and polynomials which have finite orders, then if you expand that one as you've done in high school math, then after sorting them up, you have what? Z squared minus 1/2 z minus 1 plus 1/2 z inverse. Now, what would be the signal x? According to your definition of z transform, what are they? X of -2 z squared plus x of -1 z, x0, x1 z to the -1, blah, 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 right? Now, you compare this one with that one. Then, you may say that, hey, x of -2 must be 1, x of -1 must be -1, x0 must be -1, x1 must be 2. Now, using delta functions, you can write it, right? 1 times delta of n plus 2, -1/2 times delta of n plus 1, and -1 times delta of n, 1/2 times delta of n minus 1. By the way, here, what would be the reason of convergence? It does not specify, but since you have this expression already, the reason of convergence must be the entire complex plane except the origin. And this expression also matches with your observation, right? Z cannot be 0. For all other complex numbers, it's okay. That's why you just compare the coefficients, right? When I was a high school student, one of my friends asked me, hey, Junho, suppose you have this equation. What can you say? And I said, okay, A equals D, B equals E, and C equals F. And he said, wrong. Why? Because probably he wanted to emphasize this. If this holds, right, for all x real, then we can say this. Otherwise, we cannot say that. For example, as you know, usually this says what? Find the x that satisfies this equality. They are different story, right? How many equalities do you have? Uncountably infinite. How many equality do you have? 1. Got it? So in this case, how many equalities do you have when you compare this one and that one? Uncountably infinite, because complex numbers, the set of complex numbers except the origin, has uncountably infinite numbers, complex numbers. So you can just directly match the coefficients. Done. Got it? Anyway, now this is simple. And here goes something little bit weird. But now let's see. A discrete time signal has Z transform equals log, probably natural log, ln if you want, log 1 plus a z inverse, and the reason of convergence is outside the circle of radius a, absolute value of a. Now, what can you do? And you know the Taylor series expansion of log 1 plus x. What is that, by the way? You find it. Anyway, so by writing this as Taylor series, and replacing x with a times z inverse, then you have what? Power series in z inverse, right? Now, if you remember this one again, power series in z inverse may tell you that, hey, the signal is causal and z to the 0 coefficient must be x0. Z to the negative 1's coefficient must be x1, blah, blah, blah. And you can find x that is causal. Got it? There are many ways to find the series expansion, and we will see later. Anyway, here goes the Z transform properties. So these are just assumptions we are going to use when we talk about this thing, especially for the first thing, linearity. So what we say here is that Z transform is a linear operation. What does that mean? What does that mean by linear operation? Linearity is this one. Suppose you have something that accepts, for example, here, signal, and generates another signal in Z. And we say that this box actually does Z transform. Now, what's the meaning of linearity of this box? Suppose you have x1 and obtain capital X sub 1. And suppose you have same transformation. Now you have x2 and capital X sub 2 of z. Now, same transformation with a1 x1, a2 x2. So now you have linear combination of inputs. Then linearity says the output must be linear transformation of what? The outputs. But here, you must feel something uncomfortable because Z transform is not just about this mapping rule, but with reason of convergence. So here goes reason of convergence 1. And here goes reason of convergence 2. Now, when you say that Z transform is a linear operator or satisfy linearity, then what about this reason of convergence of the linear combinations Z transform? Got it? So here, not just hey, Z transform satisfies linearity, but you have to pay attention to, so what is the reason of convergence after you apply linear combination to the input? Got it? And you may just simply say, the reason of convergence may be intersections of these two. because on the reasonable convergence of the first one and on the reasonable convergence of the second one, if they are intersected and if this is not an empty set, on this set, this converges, that converges, so everybody's happy. The problem is that, as you see, you have linear combination, then the output expression is linear combination. So far, so good. But here goes something interesting. The reason of convergence now contains the intersection. So intersection of the linear, reason of convergences may be the reason of convergence of the linear combination, but sometimes, not always, sometimes a bigger set that contains this intersection may be the reason of convergence. Now let's see why this happens. The simplest idea is this one. Suppose x1 equals a to the n u of, let me see, be careful. Just a second. Yeah, I've written some example somewhere. Just a second. Okay, got it. So let's consider this one. Suppose you have x1 that is delta of n plus delta of n minus 1. Means you have impulse at 0 and another impulse at 1 and all zeros. Now you have x2 that is negative delta of n minus 1. So you have negative 1 at n equals 1. Now let's consider z transform of the first one. And the first term becomes 1 and second term becomes z inverse. So the reason of convergence is this one, right? What about x2? x2 is negative z to the negative 1 and the reason of convergence is that one. So they have the same reason of convergence. Now let's sum them up. Then your x signal is simply delta of n, and this signal has reason of convergence as the z transform 1 for all z. And z now can be 0, right? So this simple example, too simple example, gives you an idea. Hey, when we sum up two signals, reason of convergence may be bigger than the intersection of the reason of convergences. Because they have the same reason of convergences, intersected, they are the same. Z just not 0, but as you see, the new reason of convergence is bigger. Got it? And why this happens? Let's see. Suppose you consider summation of two expressions. So the first one is 1 plus z inverse, and second one is negative z inverse. And since z is not 0, we can rewrite the first one as what? So this one is what? 1 plus 1 over z, and this is something like this, right? So the first term is 1 plus z divided by z. And what was second one? Negative z inverse. Now, let's use z in the common denominator. And what do you have? You have 1 plus z minus 1. So you have z over z. And z over z, if z is not 0, you can divide by z, right? So this is allowed if z is not 0. And we've already said that z is not 0. And here we have 1. And you may say that, strange. But as you see here, if you start from the summation of the signals, then Z can be 0. What happened? Here, your pole at the origin is cancelled by 0 at the origin. So even though from here to there, Z cannot be 0, but actually, as you see from the definition of Z transform, that is allowed. Why? Because there occurs pole 0, so-called pole 0 cancellation. So when pole 0 cancellation occurs, you may have a bigger region of convergence than the intersection of region of convergences. This is one of the examples. So remember this one, because it is very, very confusing. Here was something more complicated than this simple example. So here, this is what we've already seen in the previous class meeting. So we have from 0 to n minus 1, some exponentially increasing terms, but all zeros. Now, we use the partial sum formula of a geometric progression, and we can find this expression. We've already seen this one, right? So here, capital X of Z can be written this way. But as I told you, this expression holds when you have A non-zero. Where A is, sorry, Z is not A. Z equals not A. When Z equals A, here you have all ones. So you have that one, right? Now, let's see this one. If you just take a look at this one, how many zeros and how many poles, and where they are located. And you may say that, okay, here we have n minus 1th order pole located at the origin. If n equals 16, you have 15th order pole here, right? And now, what about the numerator? Z to the n minus a to the n. As you already know from high school math and also some engineering math or complex analysis, what you need to do is that you divide the circle with radius absolute value of A right? And then you have, for example, if A is some complex number here, from here you divide the 2 pi into, capital N. So you have 2 pi over N, another one, something like that. These are solutions to this equation. Now, in this example, we assume A is real, positive. So here, this point is A. That's why the textbook starts from here, and this one is 2 pi over 16, which is pi over 8. Got it? So at every pi over 8, you have what? Zeros of that one. And if we just take a look at the numerator, we also have 0 at A. However, as you see here, you have a pole at A, and what happens? Actually here, even though this expression do not allow us Z equals A, precisely speaking, it is allowed because the case with Z equals A is handled here. So you can just delete Z minus A Is it? Yeah. To take care of this one, what happened? We call this phenomenon as pole zero cancellation. Same as the previous. As far as you have non-zero term factors in the numerator and denominator, you can cancel. If that occurs in the rational function of z, what happens? You cancel a pole with a zero. Got it? So it's pole zero cancellation. Okay, what else? Now let's take a look at the sixth property. Let me magnify. Suppose capital X of n sequence has Z transform capital X and reason of convergence capital R sub X. Now, we assume this signal is complex valued. So, real part is a real valued signal. Let's say this is Y. Now, the question is, find the Z transform of Y in terms of the Z transform of X and its reason of convergence. And you may say that, well, I don't know, but the trick is this one. If you have a complex number, then what can you say? Its real part is simply Z plus Z conjugate divided by 2. Its imaginary part is what? Z minus Z conjugate divided by 2J. Here, J is the square root negative 1. Got it? So, even though apparently it has a single term, actually you have two terms. Summed up. And when you have two terms, it's a kind of linear combination. So let's say that this is x1 and this is x2. And if you go back to this one, right? The reason of convergence, you intersect and the resultant reason of convergence may be bigger. Same thing happened. And here, interesting thing is this one. As you see in the previous fifth property, the reason of convergence of the X conjugate signal is the same of the reason of convergence of X. Why? Why, by the way? Why? Why is the fifth property true? Just let's use the definition. So, right? This is the relation of xn and capital X and R sub X. Now, let's think about X conjugate. Then you have what? X conjugate of n, z to the negative n, right? Now, what do you want to do to remove this one? What you can do is that z conjugate equals z. So, the z transform of X conjugate can be written this way. And you may wonder, oh, what is this one? What is that one? And one of the properties you learned in high school complex numbers is that what? Something like this, as far as n is an integer. So this one can be understood as that one. Got it? Now, What is the relation between Z and Z conjugate? Z and Z conjugate have the same magnitude, but with opposite angle. What does that mean? They lie on the same circle with the circles with the same radius. And you know that from the Z transform property, if some point is in the region of convergence, then if you draw a circle, then all the complex numbers are in the region of convergence. What does that mean? This converges on the same set. Right? That's why this is true. Then by combining 1 and 5, you have 6. Got it? Similarly, by combining 1 and 5, you may have 7, where you find the Z transform of the imaginary part. Got it? What else? This is about the time reversed complex conjugate. So let's think about the time reverse first. What happens if you reverse the time? So the question is, before we talk about this one, what is the Z transform of X time reversed? And again, what you need to remember is the definition. And if you replace n with negative k, then what happens? You have this one. And now you know that for some, suppose this converges for some Z. Then what about that one? If Z0 is non-zero, then this converges on 1 over Z0. That's why you have something like this without this conjugation. And now you know that putting conjugation does not change the reason of convergence. That's why you have this result. Got it? Anyway, so 8 is simple. And what about 2? What about property 3 and 4? Actually, just use the definition. In the form of infinite sum, always, okay? Do not try to go directly to some rational function form. That causes the trouble, according to my experience. The last one, the ninth property, is actually most interesting. And here, x1 has region of convergence Rx1, x2 has region of convergence Rx2. Now you convolve, and from your knowledge about convolution in time and multiplication in frequency domain, and the Fourier transform can be interpreted as a special case of Z transform, you may quickly understand why this is true. But as I told you, this is not the older story. Let's see the reason of convergence. It again says that the new reason of convergence contains the intersection of two. Why? The story is like this. When you find R sub x1, some of the complex numbers may not allow the infinite sum to converge. When you find R sub x2, some of the complex numbers didn't allow convergence of this form. However, after you convolve and obtain new signal, let's say y, sigma y of n z to the negative n, may converge outside the intersection of these two by, again, pole zero cancellation. Okay? So you will see some examples later. And this is actually very interesting idea. The pole zero cancellation is an interesting idea because around the pole, when complex number is around the pole, you have very large output. And that may make your circuit unstable, theoretically, very large number. But practically also, that's not good because when we build some circuits, digital circuits, usually the current or voltage level is not just allowed to be as large as possible. Within some reason, it's well modeled as our mathematical model. If the value goes up very large, actually it does not go up. It saturates sometimes. And that causes a lot of trouble. Large number in your mathematical model, maybe some practical trouble in your mathematical model when you analyze. So one of the ways is to put some system before your or after your, usually before in that case, system, so that this pole is cancelled by the zero of the kind of your compensating system. So pole zero cancellation can be used to make your system more stable. Anyway, by the way, here goes another one. So we've seen this example already here. Where is this? Yeah, here. Capital X equals log 1 plus AZ inverse and this reason of convergence. And you may say that same problem. Yeah. But now, let's use these properties. Not just use power series directly. Okay. Of course, we need power series anyway. But so let me give you a hint. So what we do is that here we use differentiation of Z transform as a function of Z. And you know how to differentiate logarithmic function as far as they are real. But as you learned in complex analysis, people, including the great mathematician Cauchy and some Euler or those people, they have extended the domain of our transcendental functions, such as exponential function or logarithmic function, to complex domain with the notion of analytic function or something like that, right? And probably you remember Cauchy-Riemann condition or something like that. So they have successfully extended the domain of our kind of elementary functions to complex domain. Not only that, they have shown in many cases your ordinary differentiation of real valued function of real number, ln of x, differentiated 1 over x, something like that. You know that, right? That still holds for complex numbers. And you can apply that result here. So you differentiate, then you have negative az to the negative 2 divided by 1 plus az inverse. And then you multiply z and do some blah, blah, blah thing to get the same result. Got it? Okay. Okay, here goes section 3.5 so that you can do the Fibonacci sequence problem. So far, we mostly focus on Z transform. And Z transform just does what? Conversion of a discrete time signal or sequence into an algebraic equation, right? Polynomial in Z and Z inverse. That's it. However, we want to use this Z transform to analyze and design discrete time systems, especially linear time invariant systems whose not only LTI, whose IO relation given by what? Linear constant coefficient difference equation. For this small set, you may say small set, but it could be very large if we just design almost everything in this way. We can do a lot, like we love convolutional neural net, right? We apply everywhere and have found that as far as you have enough depth, not width, depth, then it could be a very good function approximate. So sometimes your nonlinear function may be trained from big data. Sometimes your function that is driven by random number generator to generate another random variable. This function may be complicated, but it could be learned from big data, something like that. And that is what's going on right now. So convolutional neural net is very, very good to do a lot of things, right? Image recognition, classification, blah, blah, blah. Not just as long as not alone the neural net. Similar thing as happened in the design and analysis of LTI systems. I'm not saying that every DT-LTI system can have IO relation describable by LCCDE. I'm not saying that. However, many LTI systems can be well approximated by LCCDE. In that case, our use of Z-transform allows us a lot of good things. We can use this Z-transform as a very nice tool to design and analyze the system. So let's see. Here we start from this convolution property of Z-transform. Means that the Z-transform of the convolution is the multiplication of Z-transforms. And as you know that the reason of convergence of this output may be bigger than the intersections of the reason of convergences. Now, this is just for every DT system, if we view this as the impulse response of an LTI system. We can interpret Y as the output DT signal, X as input DT signal, and H as the impulse response of the DT-LTI system. But as I told you, this Z-transform of the impulse response may be, not always, a rational function in Z or Z inverse. This is what we want. Okay? Then, in that case, it's very, very powerful. And let's see. So here, the Z-transform of some DT-LTI system has expression like this and reason of convergence this way. Actually, from this one, you can immediately find the impulse response, right? What is that? A to the n, U of n. Now, suppose the input signal has Z-transform this way. Now, what is the output signal? And we know that the multiplication of these two gives us that one. And partial fraction expansion allows us rewrite the equation in that way. Now, this is constant. And this one intersected by that one, right? And here, one of the assumptions is that A has radius less than 1. So intersection greater than 1. So intersection includes this one. Now, what can you say? Inverse transform gives us one signal, and another transform gives us another signal. This is all one, right-sided, and this is exponential. So you can easily find the output without convolving two exponential signals. By the way, if you look up the 수학의 정석, the math book in high school, actually you've done convolution of exponential sequences. Actually, there are some problems like that. Anyway, so what I want to say is that when we analyze and design the input and output and impulse response of the DTL type system filtering DT signal, we can use Z transform. And that gives us a very good thing. Why? Because the system is a dynamic system, which means that generates time varying signal. However, as you see, what's varying here? These are algebraic expressions. So Z transform allows us to rewrite dynamically varying signal and dynamically varying system as rational, sometimes rational functions in Z. Then your algebraic technique, manipulation, gives you the solution. Similar to what you learned in differential equation. When you solve differential equation, your dynamical system can be rewritten by using the characteristic polynomial or something as algebraic form. And you can easily solve the problem. Anyway, we will be finishing this one next week, but you will see the Fibonacci sequence problem in the homework. That's all for the day.